Good evening. Today we have questions on simple stresses and strengths. Temperature stresses, we are going to consider three problems. We have taken three different problems. So in this first, we have this is a composite bar is rigidly fitted at the supports A and B as shown in figure. Determine the reaction at the support when the temperature rises by 20 degrees. So values are given in this fashion. So we have that is E actually for steel we have 200 giganewton means 200 Newton per mm square, and for aluminum we have 100. So that are all values are shown in the diagrams. Then given data we have that is bars in series. Given data we have shown in the diagram, and bars when we have bars in series we have this formula L1 alpha 1 T plus L2 alpha 2 T. So here L1 we are going to say that is of aluminum. Then we have alpha also of aluminum, and then L2 means we are going to consider as steel. And then we are going to substitute these values actually. So 1000 we have aluminum 11 into 10 raised to minus 6 for aluminum 20, that is same for both. 3000 for steel 12 into 10 raised to minus 6 for steel into 20, and then PL upon AE. So this is aluminum, and then we have for steel. And then if you will solve this, we are going to get this value that is for P, which is 14.1 kilonewton value. And then we have this P, which is for both, and therefore my reactions for at both supports, that is at A and at B, we are going to get reaction of the support is same. That is 14.1 kilonewton. That is reaction at supports, because we have summation fx equal to 0, fy 0, and now as we have temperature increase, so automatically we have reactions as compressive reactions. Means if we will plot this reaction 14.1 kilonewton, then we are going to get 14.1 Ra in this fashion, and at B we are going to get in this fashion, and by this we will get summation fx equal to 0. Then we will have second problem, and in this second problem we have that is concrete column 300 by 300 millimeter reinforced with 6 steel bars each of 22 diameter. Knowing that rod is initially unstressed, determine the normal stresses developed in steel and concrete. Here we have to also find the stresses in this one. And now in this we have bar as part your column, that is in this one we have concrete and steel. So we have these bars in parallel or materials in parallel, and then we have L alpha 1 T minus L alpha 2 T PL upon AE1 PL upon AE2. Now here I have mentioned it as alpha steel, and from this we have to subtract concrete. So we know, so whichever is greater S value we have in compression, and its value that is going to be reduce actual deformation when it will keep free. And therefore if we will take P upon AE on left side, then we are going to get it as minus, and alpha c if we will take right, then we these both are added. So now here you can see L we have same for all, therefore we have cancelled L from this, and then we are going to get this formula. Now we have actually this as equal to, so we have to multiply it by 6 because we have 6 bars. So 6 into pi by 4 into 22 square, then we will get 2280.8 mm square. AC we have total concrete area 300 by 300 minus we have to subtract area of bars, and that comes 8771.19.2. And then we have, by substituting values in the equation, we are going to get from this value of P, and we got this value of P 89.27 kilonewton. To find the stress in steel and concrete, we have simply sigma s P upon AS, and that we have sigma P value 89.27, and AS, that is area of steel, we have seen 6 bars 2280.8 gives us 39.14 MPa. Now as my alpha s value is greater than alpha c, so we have compression in this. And then we have second, that is sigma c, which is P upon AC, and that is 89.27 divided by area 87719.2, that we have over here. And from this we will get 1.02 MPa, as we have alpha c less than alpha s, so we are going to get tension in this bar. So we have, sorry, concrete, so we have concrete in tension and bars are in compression. Now we have third is steel bar 16 diameter, 2 meter long, 30° initial we have temperature, and then it is increased to 150°. We have to find free expansion, then temperature. If we prevent total, we will prevent the expansion of the bar, and then stresses if we are going to prevent after 2.5 MPa. So we have first pre-expansion simply delta L alpha L equal to L alpha T. So we have L 2000 alpha 12 into 10 raised to minus 6 T. We have from 30 to 150, 120°, and delta L we will get 2.88 millimeters. Now expansion of the bar is prevented. Then we know we have formula sigma is equal to alpha TE. Now in this we have expansion delta L 2.22 and free expansion of the bar. So what will be stresses in this? So we have stresses are zero because we are allowing free expansion. Then expansion of the bar is prevented, then we are going to get in this compressive stresses, and formula we know alpha TE, and then that will be 288 MPa. That will be my uh, stress in bar when we are going to prevent is fully. And third part, we have expansion, we are allowing up to 2.5 millimeter. We have seen expansion is 2.88 millimeter, we are allowing 2.5, so we are going to restrict only 0.38 millimeter. So for temperature 2.5 millimeter, we require delta L 2.5 millimeter, temperature we require that we are going to calculate it from delta L is equal to L alpha T, and from this we are going to get temperature required for 2.5 millimeter expansion, and we will get this value. So when my temperature is to 104.17 degree centigrade, then bar is going to be 2.5 millimeter, and now we are going to prevent its expansion. And then for remaining temperature, that is after 134.17 degree to 150°, expansion is prevented, and then we are going to get stresses in this, and then we have in that case 150 minus 134.17 into 10 200 into 10 raised to 3, and that value comes 37.99 MPa, and that we can say as 40 MPa. And likewise we are going to get, or we have these three when we are going to be free expansion, when we are going to prevent expansion, and when we have partially expansion and then partially stresses. So these are the answers of your exercise number 2, simple stresses and strains. So today we will stop here only. Thank you.